How's that again? Presents the truth about earthquake prediction. Earthquake prediction is a branch of the science of seismology concerned with the specification of the time, location, and magnitude of future earthquakes within stated limits, and particularly the determination of parameters for the next strong earthquake to occur in the region. Earthquake prediction is sometimes distinguished from earthquake forecasting, which can be defined as the probabilistic assessment of general earthquake hazard, including the frequency and magnitude of damaging earthquakes in a given area over years or decades. Not all scientists distinguish prediction and forecast, but a distinction is useful. Prediction can be further distinguished from earthquake warning systems, which, upon detection of an earthquake, provide a real-time warning of seconds to neighboring regions that might be affected. In the 1970s, scientists were optimistic that a practical method for predicting earthquakes would soon be found, but by the 1990s continuing failure led many to question whether it was even possible. Demonstrably successful predictions of large earthquakes have not occurred, and a few claims of success are controversial. For example, the most famous claim of a successful prediction is that alleged for the 1975 Haicheng earthquake. The later study said that there was no valid short-term prediction. Extensive searches have reported many possible earthquake precursors, but, so far, such precursors have not been reliably identified across significant spatial and temporal scales. While part of the scientific community hold that, taking into account non-seismic precursors and given enough resources to study them extensively, prediction might be possible, most scientists are pessimistic and some maintain that earthquake prediction is inherently impossible. These are predictions, or claims of predictions, that are notable either scientifically or because of public notoriety, and claim a scientific or quasi-scientific basis. As many predictions are held confidentially, or published in obscure locations, and become notable only when they are claimed, there may be a selection bias in that hits get more attention than misses. The predictions listed here are discussed in Susan E. Huff's book, Predicting the Unpredictable, The Tumultuous Science of Earthquake Prediction, 2010, and Robert J. Geller's paper, Earthquake Prediction, A Critical Review, December 1997. The M7.3 1975 Haicheng earthquake is the most widely cited success of earthquake prediction. The ostensible story is that study of seismic activity in the region led the Chinese authorities to issue a medium-term prediction in June 1974, and the political authorities therefore ordered various measures taken, including enforced evacuation of homes, construction of simple outdoor structures, and showing of movies out of doors. The quake, striking at 1936 CST, was powerful enough to destroy or badly damage about half of the homes. However, the effective preventative measures taken were said to have kept the death toll under 300 in an area with population of about 1.6 million, where otherwise tens of thousands of fatalities might have been expected. However, although a major earthquake occurred, there has been some skepticism about the narrative of measures taken on the basis of a timely prediction. This event occurred during the Cultural Revolution, when belief in earthquake prediction was made an element of ideological orthodoxy that distinguished the true party-liners from right-wing deviationists. Record-keeping was disordered, making it difficult to verify details, including whether there was any ordered evacuation. The method used for either the medium-term or short-term predictions, other than Chairman Mao's revolutionary line, has not been specified. The evacuation may have been spontaneous, following the strong M4.7 foreshock that occurred the day before. A 2006 study that had access to an extensive range of records found that the predictions were flawed. In particular, there was no official short-term prediction, although such a prediction was made by individual scientists. Also, it was the foreshocks alone that triggered the final decisions of warning and evacuation. They estimated that 2,041 lives were lost. That more did not die was attributed to a number of fortuitous circumstances, including earthquake education in the previous months, prompted by elevated seismic activity, local initiative, timing, occurring when people were neither working nor asleep, and local style of construction. The authors conclude that, while unsatisfactory as a prediction, it was an attempt to predict a major earthquake that for the first time did not end up with practical failure. The Parkfield earthquake prediction experiment was the most heralded scientific earthquake prediction ever. It was based on an observation that a Parkfield segment of the San Andreas Fault breaks regularly with a moderate earthquake of about M6 every several decades. 1857, 1881, 1901, 1922, 1934, and 1966. More particularly Bocken and Lind, 1985, pointed out that, if the 1934 quake is excluded, these occur every 22 years, plus or minus 4.3 years. Counting from 1966, they predicted a 95% chance that the next earthquake would hit around 1988, or 1993 at the latest. The National Earthquake Prediction Evaluation Council (NEPEC) evaluated this, and concurred. The U.S. Geological Survey and the state of California therefore established one of the most sophisticated and densest nets of monitoring instruments in the world, in part to identify any precursors when the quake came. Confidence was high enough that detailed plans were made for alerting emergency authorities if there were signs an earthquake was imminent. In the words of The Economist, never has an ambush been more carefully laid for such an event. Year 1993 came and passed without fulfillment. Eventually there was an M6.0 earthquake on the Parkfield segment of the fault on 28 September 2004, but without forewarning or obvious precursors. While the experiment in catching an earthquake is considered by many scientists to have been successful, the prediction was unsuccessful in that the eventual event was a decade late. The 1989 Loma Prieta earthquake, epicenter in the Santa Cruz Mountains northwest of San Juan Bautista, California, caused significant damage in the San Francisco Bay Area of California. The U.S. Geological Survey, USGS, reportedly claimed, 12 hours after the event, that it had forecast this earthquake in a report the previous year. USGS staff subsequently claimed this quake had been anticipated. Various other claims of prediction have also been made. Ruth Harris, 1998, reviewed 18 papers, with 26 forecasts, dating from 1910 that variously offer or relate to scientific forecasts of the 1989 Loma Prieta earthquake. In this case no distinction is made between a forecast, which is limited to a probabilistic estimate of an earthquake happening over some time period, and a more specific prediction. None of these forecasts can be rigorously tested due to lack of specificity, and where a forecast does bracket a correct time and location, the window was so broad, e.g., covering the greater part of California for 5 years, as to lose any value as a prediction. Predictions that came close, but given a probability of only 30%, had 10 or 20-year windows. One debated prediction came from the M8 algorithm used by Keylesbrook and Associates in for forecasts. The first of these forecasts missed both magnitude, M.5, and time, a 5-year window from 1st January 1984 to 31st December 1988. They did get a location, by including most of California and half of Nevada. A subsequent revision, presented to the NEPEC, extended the time window to 1st July 1992, and reduced the location to only Central California. The magnitude remained the same. A figure they presented had 2 more revisions, for n greater than or equal to 7.0 quakes in Central California. The 5-year time window for one ended in July 1989, and so missed the Loma Prieta event. The second revision extended to 1990, and so included Loma Prieta. When discussing success or failure of prediction for the Loma Prieta earthquake, some scientists argue that it did not occur on the San Andreas Fault, the focus of most of the forecasts, and involved dip-slip, vertical movement rather than strike-slip, horizontal movement, and so was not predicted. Other scientists argue that it did occur in the San Andreas Fault zone, and released much of the strain accumulated since the 1906 San Francisco earthquake. Therefore several of the forecasts were correct. Huff states that most seismologists do not believe this quake was predicted per se. In a strict sense there were no predictions, only forecasts, which were only partially successful. Ivan Browning claimed to have predicted the Loma Prieta event, but this claim has been rejected. At 03:32 on 6 April 2009, the Abruzzo region of central Italy was rocked by a magnitude M6.3 earthquake. In the city of L'Aquila and surrounding area, around 60,000 buildings collapsed or were seriously damaged, resulting in 308 deaths and 67,500 people left homeless. Around the same time, it was reported that Gianpaolo Giuliani had predicted the earthquake, had tried to warn the public, but had been muzzled by the Italian government. Gianpaolo Giuliani was a laboratory technician at the Laboratory Nazionale del Gran Sasso. As a hobby, he had for some years been monitoring radon using instruments he had designed and built. Prior to the L'Aquila earthquake, he was unknown to the scientific community and had not published any scientific work. He had been interviewed on 24 March by an Italian-language blog, Don Democratici, about a swarm of low-level earthquakes in the Abruzzo region that had started the previous December. He said that this swarm was normal and would diminish by the end of March. On 30th March, L'Aquila was struck by magnitude 4.0 trembler, the largest to date. On 27th March, Giuliani warned the mayor of L'Aquila there could be an earthquake within 24 hours, and an earthquake approximately equal to 2.3 occurred. On 29th March, he made a second prediction. He telephoned the mayor of the town of Sulmona, about 55 kilometers southeast of L'Aquila, to expect a damaging, or even catastrophic, earthquake within 6 to 24 hours. Loudspeaker vans were used to warn the inhabitants of Sulmona to evacuate, with consequential panic. No quake ensued and Giuliani was cited for inciting public alarm and enjoined from making future public predictions. After the L'Aquila event, Giuliani claimed that he had found alarming rises in radon levels just hours before. He said he had warned relatives, friends and colleagues on the evening before the earthquake hit. He was subsequently interviewed by the International Commission on Earthquake Forecasting for Civil Protection, which found that Giuliani had not transmitted a valid prediction of the main shock to the civil authorities before its occurrence. As the preceding examples show, the record of earthquake prediction has been disappointing. The optimism of the 1970s that routine prediction of earthquakes would be soon, perhaps within 10 years, was coming up disappointingly short by the 1990s, and many scientists began wondering why. By 1997 it was being positively stated that earthquakes cannot be predicted, which led to a notable debate in 1999 on whether prediction of individual earthquakes is a realistic scientific goal. Earthquake prediction may have failed only because it is fiendishly difficult, and still beyond the current competency of science. Despite the confident announcement 4 decades ago that seismology was on the verge of making reliable predictions, there may yet be an underestimation of the difficulties. As early as 1978 it was reported that earthquake rupture might be complicated by heterogeneous distribution of mechanical properties along the fault, and in 1986 that geometrical irregularities in the fault surface appear to exert major controls on the starting and stopping of ruptures. Another study attributed significant differences in fault behavior to the maturity of the fault. These kinds of complexities are not reflected in current prediction methods. Seismology may even yet lack an adequate grasp of its most central concept, elastic rebound theory. A simulation that explored assumptions regarding the distribution of slip found results not in agreement with the classical view of the elastic rebound theory. This was attributed to details of fault heterogeneity not accounted for in the theory. Earthquake prediction may be intrinsically impossible. In 1997, it has been argued that the Earth is in a state of self-organized criticality where any small earthquake has some probability of cascading into a large event. It has also been argued on decision-theoretic grounds that prediction of major earthquakes is, in any practical sense, impossible. In 2021, a multitude of authors from a variety of universities and research institutes studying the China seismoelectromagnetic satellite reported that the claims based on self-organized criticality stating that at any moment any small earthquake can eventually cascade to a large event do not stand in view of the results obtained to date by natural time analysis. That earthquake prediction might be intrinsically impossible has been strongly disputed, but the bestest proof of impossibility, effective earthquake prediction, has yet to be demonstrated.